So thanks, Costa, for that introduction. Thanks to the organisers for the honour and privilege of being here today, talking to such a great crowd in the room, but also online. And I would also like to acknowledge the traditional owners of the lands on whom we meet, the Gadigal clan of the Eora Nation, and to note that they themselves have lived through climate change, through the last glaciation, the deglaciation, and now human-induced climate change. Now, what I'll be talking about today is the power of land care in relation to climate change, both from an adaptation point of view and an emission reduction point of view. And I've deliberately put a small L in front of land care here and throughout my presentation, because for me, whilst the organisation is critical, it's the idea, the concept of land care which is powerful and persistent, and it's an idea for our times. Now, when I put this picture up, it was actually to tell the story of my presentation. So what I'll start with are the dark clouds that we often hear about in terms of climate change. But we also need to note that there is blue sky, there is sunshine, and here within this group, we have a vision, which is the rainbow. We have a pathway towards that vision, and we know we're not going to tread that pathway alone. So when we look at climate change, the unfortunate reality is we are not on track for 1.5 degrees. We are far off track for 1.5 degrees, which is the lower end of the Paris Agreement goals. This is a graph coming from the International Energy Agency, which is hardly a conservative organisation, or radical organisation, I should say. It's very conservative. And it shows the carbon dioxide emissions from electricity in industrial sectors going back over 100 years. And what you can see is it's gone up massively over time. Things like the global financial crisis and COVID have made little blips, but they're very temporary. We bounce back very, very quickly on track towards increasing emissions. And last year after COVID, we bounced back, just like we did after the global financial crisis. We had record greenhouse gas emissions last year. And that's led to record greenhouse gas concentrations in the atmosphere. We're now 421 parts per million. That's 50% higher than it was pre-industrially. And it's not just carbon dioxide, but it's also methane and nitrous oxide and various other greenhouse gases which are at record concentrations. Things like methane are triple pre-industrial concentrations. And importantly, we have to take this curve, not just flatten it, we have to take this down to zero. That's where the net zero that you often hear politicians talking about comes from. And that's because when we emit a tonne of this carbon dioxide, roughly speaking, a quarter of it gets absorbed in the ocean, a quarter of it gets absorbed by the land, trees and grass, the things that you're involved in particularly, and around half of it sits in the atmosphere. And it will sit in the atmosphere for hundreds and up to thousands of years. And the only way we can stop that accumulation in the atmosphere is by taking this down to zero, and as I'll show you, below zero. And we're way, way far from that. Now, when we look at what's already happening because of these increased atmospheric concentrations of greenhouse gases and the climate that's already generating, we're around 1.24 degrees above pre-industrial on a trend basis. So to put this in context, our last glaciation period, what people call the Ice Age, was around 5 degrees colder than our historical period, historical temperatures. That's 5 degrees gives us a glaciation. 5 degrees gives us sea levels 120 metres below what they are currently. That's why people could move from the mainland to Tasmania. They could move from Papua New Guinea to the mainland. They could move from Europe to the UK because all they had to do was walk. That was what 5 degrees does to the world. So we're already a quarter of the way towards a glaciation sort of range of temperature, but obviously in the other direction. So 1.24 degrees might not sound much, 1.5 degrees might not sound much, but it is huge in terms of global temperatures. Now, we can't really conceive that we do that sort of change, a quarter of a glaciation's worth of change, and not have impacts across the globe. And that's exactly what this graph from the IPCC shows. It shows studies, the locations of studies which are already demonstrating climate change impacts. And you can see that you can't go to any continent, there's no island group, there's no ocean, there's no sector which is not impacted already by climate change. And looking at a couple of things which are important to Landcare, agricultural productivity is already being hit, and hit big time by climate change. This is a recent study which looked at agricultural statistics, and it took out the technology improvement, the management improvement signals, and looked at the climate change signal. And what that shows is, on average across the globe, we're down agricultural productivity about 20% compared with what we would be in the absence of climate change. And you can see that that's not evenly distributed. Some places, the old USSR, Canada, is benefiting from climate change. Most of the world isn't. And our region, Africa and Central America, are really badly hit already by climate change. And this will just mount. And the challenges of feeding the world but looking after our land resources will just increase over time if climate change is let rip. And this is also not just the averages, which that previous graph showed, but it's also looking at the variability. Again, this is a graph from the IPCC, looking at food shocks to the system. So climate is only one of the drivers of food shocks. There's others, such as the Ukraine war, which we're experiencing. But just shows for crop and livestock systems the areas where the shocks are particularly big, but also the frequency of those shocks. And you can see from the graphs on the right that we're seeing not only more frequent food shocks, but they're actually getting bigger and bigger over time. And right now, we're in another one of these. So there's no room to be sanguine about this. It's hitting us hard already. And as we remember from the Black Summer fires and also Black Saturday and various others, we know that fire risk here is increasing, as it is globally. And when we look at the Australia situation, almost every indicator of fire risk is getting worse. So whether it's the fire season, which is extended, effectively we're now in a fire year in many parts of Australia. Fire intensity and frequency have got worse. Days of fire danger, high fire danger index have gone up, and the affected area has increased. When we look at the Black Summer fires, that covered around 18 million hectares, which is about 6 times the size of Belgium, to put it in context. 6 times the size of a non-inconsequential European country, and that's what burnt in that year. And if we look at those graphs on the top right-hand side, that shows where the fire danger has gone up. If we look at the ones on the left-hand side is the area burnt in Australia in our normal fire season, the summer period, and the one in the middle is what's happening in the shoulder seasons, like the winter period. And you can see that in terms of the traditional fire season, we're going up linearly in terms of area burnt, although Black Summer was a gross outlier. If we look at the winter period, that's actually going up exponentially in terms of area burnt. Again, absolutely no reason not to think about this very seriously. When we look towards the future is ours to choose. At the moment, we're choosing a future which is not great when we look at a global scale. What this shows is changes in temperature and changes in carbon dioxide concentration depending on different development and other trajectories we embark on or go on as a species. They range from the very high emissions trajectory down to the very low emissions trajectory. At the moment, at best, we're on the intermediate one, the sort of orangey colour, which will lead us to a world of roughly 3 degrees. That's 2/3 of an ice age worth of temperature, if you use that sort of metric. Really significant. Although it's way below what it could be if we let it rip and hadn't had something like the Paris Agreement. If we want to meet the Paris Agreement targets of well below 2 degrees and if possible 1.5, we have to go on the 2 bottom trajectories, what's called the very low and low on this graph. And you'll note that those trajectories do have net zero elements in them. To go to 1.5, we have to go net zero by around 2050, or now a little bit earlier than that, because we've continued to produce those emissions, as I showed you in the first graph. To stick to 1.5 degrees, that's net zero by 2045 or so. 2 degrees is net zero by at least 2070. But importantly, those lines don't stop at zero, they go below that zero line. That's what we call negative emissions. To stick to 1.5 or 2 degrees, we have to not only reduce our emissions to zero, then we have to start sucking carbon dioxide out of the atmosphere. And landcare will be a fundamental part of doing that. Looking after our land is one way of taking that carbon dioxide out of the atmosphere. Now, what happens if we actually let climate change continue roughly on the current trajectory? We end up in a world that looks like this in terms of temperature and rainfall. So this is what the world would look like at 4 degrees, which is hopefully not where we're quite going, but the patterns of change are exactly the same for 3 degrees or 2 degrees, just less intense. And you can see from the left-hand graph that's of temperature that everything warms. There is no place on Earth that doesn't, but different places warm at different rates. And importantly, the interior of the continents warms up faster than the coastal areas, and the land warms up faster than the oceans. If we look at the rainfall changes on the right-hand side, which are so fundamental to what happens in terms of our land management, we see that, again, things are different in different places. So some places get a lot more rain, some places get quite a lot less. And unfortunately, Australia is one of those places which tends to get a lot less. But really importantly, there is no one-size-fits-all, is that the combination of temperature and rainfall changes, climate change, will vary from place to place. It'll be adapting to that. We'll have to take account of those specific locational changes, that combination of temperature and rainfall change. Now, when we look at these sorts of changes and other information which is incorporated in the Intergovernmental Panel on Climate Change reports, which are about 10,000 pages worth if you really want to plough through those. But fundamental to landcare are changes that impact on almost everything that you do. So in particular, we're likely to see big changes in average rainfall, but also variability in rainfall, and I'll show you that in the next slide. And that will generate significant implications for things like drought and drought management in terms of water availability and water quality, and that does not look good, as I'll show you. In terms of fire and increased fire risk, it's already bad, getting worse. In terms of plant establishment, putting those plants in the ground and having them thrive. In terms of soil carbon, which is fundamentally driven by that combination of rainfall and temperature. As well as those changes in that seasonality and amounts of rainfall and variability of rainfall, we're likely to see increases in rainfall intensity. So as the atmosphere warms up, it holds exponentially more water. So if you think of the atmosphere as a bucket, as the temperature of the atmosphere warms up, you've got a bigger bucket. So there's two implications of that. Firstly, it takes longer to fill the bucket up before it rains. So you've got bigger gaps between your rainfall events. And when it does rain, it's a bigger dump, a lot more intensity. And that more intensity will drive things like erosion, soil erosion, flooding, events just as we've seen recently, soil contamination, where we get a movement of unwanted material, infrastructure damage, fences being torn down, etc., and the list could go on. Big challenges in terms of management of biodiversity and actually ensuring that our biodiversity lasts on our landscapes and thrives on our landscapes. Challenges in terms of pests, weeds and diseases. Not just a simple translation of them moving further south, but changes in the intensity of extreme events that often generate particular challenges in terms of weeds, etc. Challenges in terms of outside work. So as the temperature goes up, heat stress goes up, the ability to work outside goes down, at least in the middle of the day. Significant health issues if you don't look after yourself under those conditions. And of course, coastal zone erosion, and I haven't got time to cover this, but our sea levels are now going up at 4.5 millimetres a year. Last century, on average, they went up 1.3 millimetres a year. That's the acceleration of sea level rise that we're seeing. And the scale of potential sea level rise over the next 100 years or the next 300 or 400 years is in metres, not centimetres. So our coastlines are going to be really challenged. And it's not just that we've got sea level rise, we've also got increasing wave intensity right across the globe, and in every ocean basin, our average wave intensity is going up. So there's more energy on our coasts as well, more erosive capacity. And then, of course, in tropical areas, we've got tropical cyclones, which are increasing in intensity. A higher proportion of the tropical cyclones now are category 3, 4, and 5, the ones that really hit our coastlines hard. So there's a lot here. These are the dark clouds that I spoke about. But what we need to focus on, particularly in landcare, is those extreme events. And when we look at that change, particularly in relation to El Nino and La Nina, we're in a La Nina at the moment, is that we're seeing already an increase in the intensity of those events. So the disruption, both on the upside with La Ninas and rainfall and the downside with El Ninos and drought, is increasing. So our climate variability is already being affected by climate change. And what this graph showed from Scott Power from the Bureau of Meteorology shows is that it's likely to increase further in the future, and particularly if we let climate change rip. And this is just a simple version of a more complex graph in the recent IPCC report, which demonstrates very conclusively that almost every model that models El Nino shows that increase in variability of precipitation. So that difference between the wet years and the dry years is likely to increase. And that will drive many things that happen in landcare. Now, when we look at future impacts of climate change, this is a very complex graph, which it's the big picture, not the details here, we'll follow in a few graphs that are important here. But what this shows is a collation of thousands of studies looking at future climate change impacts, split up by different sectors. So on the left-hand side is a regional split. So the top line is the global picture of climate change impacts, and then it goes down to sort of continent level and then specific regional splits such as mountainous areas. And on the vertical columns is different sectors. So we have impacts on water and food on the left-hand side, then it's on health and well-being in the middle, and then on the right it's cities, well-being and infrastructure sort of issues. And you can see the overall picture from this is almost every combination of sectoral impacts in regions has a minus against it. The only cells which have a plus, which means positive impacts, are mixed. They have both, climate change has both positive and negative impacts in that sector, in that region. There is no single cell on this whole graph which only has a positive, which only shows climate change is likely to bring benefits to any particular sector by region combination. Now, if we actually look at one particular aspect of this, such as heat, oftentimes people talk about just the immediate direct effects. So yes, you're working outside, you get a lot more heat, you get potential heat stress, and think that's the limits of it. Well, heat is much, much more pervasive than that. Even in a direct sense on human health, heat events can actually result in bad health outcomes years and years later, like kidney disease as one example. But it's much more pervasive than that. When we think about health, heat also affects, obviously, our water availability. As temperature goes up, our evaporation goes up, the water availability in our rivers and dams goes down. Heat impacts on crops, so we get desiccation of crops often at the very time we're about to harvest, and you get a really nasty heat event which reduces your quality and quantity significantly. It impacts on livestock, so if you've got hot livestock, they tend to cut down on their food intake because eating generates internal heat, and if you can't get rid of that as an animal, you raise your body temperature and you get sick. So animals eat less under heat conditions, they produce less. If we look at other issues, infectious diseases are directly related to heat. So whether it's waterborne or foodborne diseases, etc., there's a heat link there. When we think about mental health, there's often a heat link there. That both acute and chronic health outcomes are related to strong heat events. And if we look on the right-hand side, there's economic implications. As temperature goes up, economic productivity goes down. So something as simple as heat has pervasive implications across our systems. And again, this will not be evenly distributed, so there's a big equity issue there, something which came out in the book that Andrew launched last night. So when we look at the top left-hand panel, that's our historical frequency of heat stress days. This is what these authors particularly call deadly heat stress days, the combination of heat and humidity which makes it difficult for someone to be outside and do anything more than a short period of light exercise before building up your internal body temperature. And if we look at the right-hand panel, the bottom right, that's what it might look like in a high emission scenario by the end of the century. Big slabs of the world and the majority of the human population will suffer almost every day being a heat stress day. And if we look at Australia, the top end will almost every day become a heat stress day. And those conditions historically experienced by the top end will spread down around a third to a half of the continent. So the environment in which we operate will be fundamentally changed. And as the last slide on these sort of dark cloud side of things is that water and water availability will fundamentally change as well. So this is another graph from the IPCC. What this shows is percentage reduction in runoff per degree Celsius change. So if we have a 3-degree change, which is where we're heading, you multiply these numbers by 3. So for example, the Murray would have something like a 60% reduction in runoff and hence inflow into our dams under that scenario on average. Of course, the variability will go up as well. And you can see that that's pretty fundamentally big right across Australia. Less so in the northwest, possibly improvements, but everywhere else, water availability is going to go down. And so if we think we've got challenges in terms of competition for water between agriculture, environment, urban and industrial uses, this is just going to get far, far more intense. We need to pay really significant attention to this now. And a Murray-Darling Basin plan or a river plan anywhere in Australia which does not take climate change into significant account will be effectively meaningless. Now, of course, in the face of these sorts of challenges, we're going to adapt. That's what humans do. We're an adaptive species. That's why we can live from everywhere from the poles to the equator. And we're going to do that with climate change, just like we do it with everything else. And again, this is a graph from the IPCC, and it shows across different sectors, down the left-hand side, the possible adaptation options. And I'll just zoom in on this so it's easier to read. These are those areas associated with landcare, so it's the land and ocean management. And on the left-hand side are different adaptation options, very aggregated ones. And then on the right-hand side, the little blue dots, is assessment of the feasibility of these adaptation options against different criteria, such as economic and technological and other criteria, based on existing literature. And importantly, you can see from that every one of those adaptation options, there's at least some degree of feasibility in terms of implementation. And importantly also, in many cases, there's a congruence between those adaptation options and emission reductions. So you can deal with both the symptoms of climate change and the causes of climate change at the same time. And I think that's a really important message. Now, coming out of this and many other studies is a recognition that adaptation responses to climate change will be highly contextual. And they'll be highly contextual not just because of that locational combination of temperature and rainfall change I talked about before, which will be different from place to place, but also because every context, every landscape, every land manager will have different goals and different resources to work with. And so that context is both a challenge, because it means that there's no one-size-fits-all solutions, but also it's a real benefit, because by trying out that massive array of options in those different contexts means you can have a huge and rich learning base from which to choose your own sets of adaptation responses. And almost all of these adaptation responses across the land and ocean sector are consistent with land care activities. And almost all of those adaptation options, as well as having benefits in terms of emission reduction, also have other benefits. So it's those co-benefits which are pervasive across land care. Almost everything you do not only has a direct benefit, but also subsidiary or co-benefits as well. And that's the same with climate change. So many of the things, whether it's building up soil carbon or improving biodiversity, not only has that direct benefit, but also co-benefits at the same time. And it's really important with adaptations to address limits and barriers. And particularly, that's potentially done through social learning. So it's learning from each other, trying out different things and learning and accelerating that learning. And importantly, when we do adaptation to climate change, we don't want to increase greenhouse gas emissions at the same time, because that's effectively self-defeating. And as well, just to reinforce this, is that co-benefits, that idea of taking landcare and implementing landcare and having many, many additional benefits, I think relates as well to the Sustainable Development Goals. And landcare actually recognises the integration of effective climate response with sustainable development. And again, this is a graph from the IPCC, and I'll just zoom in on that, the parts that relate to landcare. And you can see that almost every one of those adaptation categories in this IPCC report gets a big plus in terms of sustainable development across the 17 different sustainable development goals. So again, there's that global implication of doing landcare and generating many, many benefits for the world. Now that's the good news story. There's lots and lots of potential here to do good climate adaptation, but how are we doing? And the answer is not great. So if you actually think about this logically, what I've just shown you is that climate change impacts are really large, and they're potentially even larger. They're systemic. They go across our different systems. They're rapid. They're happening now and they're accelerating, and they're broadly net negative. There are some good aspects of climate change, but they're in the minority. And logically, when you've actually got that sort of challenge, you set up a system which responds at scale, at the appropriate scale, which means we need an adaptation response which is large, which is systemic, which is rapid, and it's very positive. And I actually think that landcare can do that. Landcare not just here in Australia, but landcare globally. Unfortunately, though, when we looked at the state of adaptation, climate adaptation across the globe, essentially climate adaptation is the poor cousin, or maybe not even the poor cousin, of emission reduction. Virtually no funding globally goes towards climate adaptation, and importantly, of that little bit that does go to climate adaptation, very, very little of it goes to the implementation side, understanding the social and cultural barriers to implementation of adaptation. There is a lot to do. And that quote down the bottom, which I should actually read out, unfortunately, most observed adaptation across the globe is fragmented, it's small in scale, it's incremental in nature, it's sector-specific, it's designed to respond to current circumstances and challenges and near-term risks rather than the long-term, and it's focused more on planning and talking rather than implementation and doing. So almost every one of those criteria falls short of what is already needed and what will increasingly be needed in the future. So moving on to the emission reduction side of the equation, is that when we look at food and agriculture, which are key sectors associated with landcare, is that food systems produce around 29% of greenhouse gas emissions globally, and it's not that far off nationally either. Now that 29% is roughly the same amount of emissions as our electricity systems produce globally or nationally. It's really, really large. It's far, far too big to ignore, and yet to date, most governments have largely ignored it. They've put it aside because it's a fairly contested area and there's not a lot of easy solutions. So what the IPCC did, is looked at the possibilities, the potential for different emission reduction options and the costs associated with that. And again, I'll zoom in on part of this graph and look at, on the top, it's essentially the energy emission reduction options and the ones associated with the land sector. And without going into huge detail, the length of those horizontal bars is essentially the potential for emission reductions, and the colour associates with the cost. So if it's a blue colour, it's either very cheap or even profitable to actually implement, such as the two top bars are wind energy and solar energy. You can make a big buck out of implementing wind and solar, as we're currently understanding now in Australia, contrary to some of the comments just made a few years ago in political circles. But if we look at the next set of big bars, they're all in the land sector. They're forest regeneration, forest management, agricultural carbon sequestration. They do have a bigger cost, so the assessment here is that they often have a positive cost, and so that cost ranges from $20 up to $100 or more a tonne, but nevertheless there is significant potential there. And the challenge that we have is to actually turn these bars from oranges to blues. And I think with good evidence, you could actually demonstrate that as a general concept. And again, what we see with the IPCC assessments is that if we do emission reduction well, it not only reduces greenhouse gas emissions, but it has broad implications and positive implications for sustainable development. This is not just about solving climate change, this is actually about solving the big problems that humanity faces. And again, focusing on just part of that graph that focuses on the land sector, you can see for key things that landcare and land carers are interested in, carbon sequestration in agriculture, looking after soils, looking after vegetation, there are big pluses against most of those sustainable development goals. The gaps in that are simply because there are in some combinations of activities by sustainable development, there isn't a good evidence base yet. So that's a challenge for us. How do we develop that evidence base so that we can actually fill this out and demonstrate those synergies? Now, my last few slides deal with carbon sequestration, because I have a growing concern that there's perhaps some degree of over-enthusiasm about carbon and carbon storage on our landscapes. And that's not at all to diss it, it's actually to recognise it, but also to recognise the limitations. And I'll talk about three things. I'll talk about priorities, I'll talk about price, and I'll talk about practicalities here. So when we talk about priorities, is that clearly our first priority in terms of emission reductions should be stopping the fossil fuel combustion and burning that we have. It's the coal and gas and oil. We should not be using at this stage of climate change once-off or potentially once-off carbon sequestration on our landscapes to give a free ride to other industries. There's a fundamental ethical issue here from my perspective. There's also an economic efficiency issue here. Is that we should be looking in the first instance at ways of decarbonising our electricity system, at decarbonising our transport, at decarbonising the heating of our buildings, etc. And those are all feasible. They're actually much more feasible than most people recognise. And it's great that now we've got a government which is actually moving on this at something like the rate at which is needed, even though some people would like it to be faster. Yes, there is a case for using carbon offsets in terms of hard-to-abate sectors, such as maybe airline flights, etc. But increasingly, we can't use that to actually have a moral hazard building up which allows them to continue doing what they're doing, not investing in alternatives, simply because they can get cheap carbon credits, some of which might be dodgy. In terms of price, when we look at the ecosystem service value of carbon, this is work by Rochelle Myers and others, oftentimes that ecosystem service value of carbon, the improvement in water infiltration, the improvement in water storage, the improvement in nutrient delivery to growing plants is greater than the climate service carbon, the $20 a tonne or whatever you need to actually send a signal to reduce emissions. And it would be even greater if you included the climate adaptation component. So when you build up your soil carbon, you have a climate adaptation response. You can store more soil water so that you actually have a buffer against higher temperatures and lower rainfall. When we're thinking about carbon sequestration, we need to incorporate the other inputs that go with soil carbon, for example. Is that when we store carbon in the soil, it's not by itself. It's also stored with nitrogen and phosphorus and potassium and sulfur. And if we really want massive soil carbon, we can add all of those other things in, but they all cost. And we need to think about that cost. If we go down a much more natural route, it's a slower generation of soil carbon, and sometimes we can get a relatively quick response simply because we've got spare, or inverted commas, spare nitrogen, phosphorus, or other nutrients in our system. But we need to take into account the price of other nutrient inputs that go with soil carbon. There's almost a fixed carbon-nitrogen ratio when you look at soil carbon. So you can't store carbon without storing nitrogen at the same time. And in many cases, when we look at this, carbon storage is a once-off. You can build up your soil carbon and then it plateaus out. You can build up your biomass, then it plateaus out. So we need to be thinking about that once-off nature of carbon storage on our landscape and thinking about when we do that. Now, if you actually look at those bottom graphs, on the left-hand side is the Australian carbon price, the accused price. We can see that it was essentially going up exponentially until Minister Taylor intervened with a change fundamentally in the rules, which plummeted that, something ICAC might want to investigate at some stage. When we look at the European situation, it hasn't had that equivalent plummet. They haven't changed their rules. We've seen essentially an exponential growth. Over in Europe, the carbon price is now $137 Australian a tonne, and it will go higher as other industries that look to offset their emissions through those offsets there. That raises a real significant question. Do we go in at the bottom of the market, or do we wait and go in when there's a higher value for our carbon credits? It's a fundamental question if you've only got a once-off option. And then there's the practicalities of soil carbon. So when you actually store carbon on your land, you can only trade that once. You can't sell that carbon credit off to a fossil fuel company and then claim that carbon credit yourself to offset your own emissions, say from livestock production. You can only use it once. When we look at the global picture, there is simply not enough land, and there never will be, to actually store the amount of carbon we're releasing each year, the 42 billion tonnes from fossil fuels. There is a fundamental physical and biological limit there. If we want to maximise carbon sequestration on our landscapes, that will result in other trade-offs. You won't get optimal biodiversity, water, regional employment, or other outcomes. You will need to undershoot that so you can actually have multiple outcomes, multiple benefits, the things that I talked about in terms of sustainable development before. If we're serious about looking at baselines, it's much more complicated than we currently think. On the first slide I put up, I said roughly a quarter of the carbon dioxide emissions that we're emitting right now is being absorbed by the land, trees, and soil. So on average across the globe, we're actually reducing those, we're sucking down carbon dioxide into our landscapes. So our baseline is not a flat line, our baseline is actually increasing on average across our landscapes. We need to think about that. We also need to think about climate change. If we're thinking about 100 years of carbon storage, climate is going to change hugely in that 100 years. And in southern Australia, trends to drier conditions, trends to hotter conditions will drive down carbon in our soils and our biomass in our landscapes. Climate is the fundamental driver of soil carbon. Management is a little bit on the top of that. If our climate changes, we need to recognise the potential vulnerability of people who have committed to carbon sequestration on our landscapes to getting paid for that, because that might reverse, not through any fault of their own. So what can Landcare do? I think a huge amount. So Landcare, in my view, is fundamental to both the adaptation response and to emission reductions, as I've shown you in my slides here. But it's really important to recognise that the land sector and the coastal zone and blue carbon, etc., by themselves cannot solve climate change. There's a tendency to push downwards to individuals and NGOs and community groups the responsibility for climate change. As a group, I think you need to push back up. You need to push back up to governments to put in place the enabling conditions to respond to climate change effectively, and also to industry to say, get your act together. We're getting our act together, you need to do the same. I think Landcare has a huge role in terms of what we heard Ella talking about before, the subsidiarity, the empowerment of locals to use their knowledge to create solutions, to test those solutions, to improve the options available to everyone so that you can adapt sensibly to climate change. And that means you can start thinking about crossing scales, transfer all of those solutions from the local to the global scale. And I think that's part of the power of Landcare. I think it's really important because you're already thinking about the future. And that's a fundamental part of thinking about climate change. And so we want to think about solutions that bring multiple benefits now as well as in the future. And I think that's in your DNA. And I think those solutions, if implemented and communicated, will celebrate and acknowledge the knowledge that you have and have accumulated both individually and collectively. And I think that's a great thing. If we do this well, and if this is enabled by government, and it's not yet there, I think we can use Landcare to promote social learning much more broadly across our societies so that we actually learn from each other about what we can do. And there's a lot of potential for that, but it's not necessarily been implementing. We don't have a national adaptation or emission reduction learning process here. It's not embedded into our education systems, yet I argue it should be. And lastly, if we're to accelerate the learning that we need in a fast-changing world, we not only have to recognise those things that work, but we have to recognise and acknowledge and document those things that don't work. Because if we don't, other people are going to go down dead ends and go down rabbit burrows that they don't need to do. And we just haven't got that much time to waste, and we haven't got the resources and goodwill that's lost when that happens. So working together to accelerate that learning, in my view, is one of the fundamental things that you can do. Thank you.